calorimeter. A calorimeter is used to measure the heat content of an object. Using this equipment, we can measure the heat produced or absorbed in a physical or chemical process. A calorimeter has two vessels, an inner vessel and an outer vessel. This way, no heat can be transferred from the inner to the outer vessel or from the outer to the inner vessel. Thus, the inner vessel is thermally isolated from the surroundings. The inner vessel is made of copper, as copper has low specific heat. The bigger, that is outer container, has a lid made of a bad conductor of heat. The lid has two holes. A thermometer for measuring the temperature is inserted through one hole, and a stirrer for stirring the liquid in the calorimeter is inserted through the other hole. Inside the calorimeter, water at a fixed temperature is placed. This means that the temperature of the inner vessel and that of the water in it is the same. When a hot object, for example say an iron object at higher temperature is placed in water, heat exchange takes place between the hot object, that is iron ball, water and the calorimeter. The process of exchange of heat stops when all the three, that is the iron ball, water and the calorimeter, reach the same temperature. As discussed earlier that the calorimeter is thermally isolated from the surroundings. The total heat lost by the hot object, that is iron ball, is equal to the total heat absorbed by the calorimeter and water inside it. If instead of a hot object, a cold object is placed in the calorimeter, then the cold object will receive heat from the water. This exchange of heat will increase the temperature of the cold object, decrease the temperature of water and calorimeter. Suppose the mass of the inner vessel in the calorimeter is mc and its initial temperature is Ti, and the mass of the water in the calorimeter is mw. As we have supposed the initial temperature of calorimeter is Ti, the temperature of water will also be Ti. Suppose we place an object of mass Mo and temperature To in the calorimeter. If the temperature of object To is higher than that of the calorimeter or water Ti, then the object will give away heat to the calorimeter and water. After a while, a time will come when the temperature of all three become the same. Let us assume this final temperature to be Tf. Suppose the total heat given away by the object is Qo. The heat gained by the calorimeter is Qc, and the heat gained by the water Qw. Then, the total heat given away by the object, which is Qo, will be equal to the sum of the heat gained by the calorimeter Qc and by water Qw. That is, Qo is equal to Qc plus Qw. We already know that amount of heat, that is Qo, Qc and Qw, depend on mass, specific heat and change in temperature, that is delta T. If the specific heat of the material of calorimeter, water and the object are Cc, Cw and Co respectively, we can write Qo is equal to Mo into delta To into Co, where delta To is equal to To minus Tf. Qw is equal to Mw into delta Tw into Cw, where delta TW is equal to TF minus TI. QC is equal to MC into delta TC into CC, where delta TC is equal to TF minus TI, which is equal to delta TW. Substituting these in equation 4, we get MO into delta TO into CO is equal to MC into delta TC into CC plus MW into delta TW into CW, and this is equation 5. We can measure all the masses and temperatures. If we know the specific heats of the material of the calorimeter, that is copper, and that of water, then the value of the specific heat of the object can be calculated using formula 5. Come, let us now solve numerical problems.